So I'm just going to be making a very short chapter 3 summary for the chemistry periodic because honestly there's nothing really much to do, and I find doing the CQDs and reading out the answers very useless because we can all do it ourselves. So I'm just going to give a short summary on some exceptions and things we need to know for the exam. So anyways, let's start. So first of all, we all know that we always have 4 types of bonds. Of bonds. Our first type is gonna be our ionic, and we describe ionic bonds as an electrostatic force of attraction between a metal and a non-metal, and it's a really strong type of attraction, and yeah, it's like one of our strongest types. So it's when it's between a metal and a non-metal, and it's the losing or gaining of electrons. Metals will always lose electrons. Non-metals will always gain electrons. When these lose electrons, they become positive because they have more protons than electrons, and when these gain electrons, they become negative. And the reason the ionic bond forms is because of the strong electrostatic force of attraction between the ions. Now our second type is gonna be our covalent bond. Now our covalent bond is it's like between a non-metal and a non-metal. And it is the sharing of electrons between the two non-metals. It can either form a single covalent bond, double covalent bond, or triple covalent bond. In this case, we are sharing 2 electrons, aka 1 pair. Here we are sharing 4 electrons, aka 2 pairs. Here we are sharing 6 electrons, aka 3 pairs. Here we have our other type, which is our metallic. And this happens between a metal and a metal. And again, it is described as an electrostatic force of attraction, but this time it's between positive metal ions and C of delocalized electrons. Nice. Now we know it's between the positive metal ions and a sea of delocalized electrons, or you could say metal cations. By the way, both work. And our last type is the weirdest one, I guess. It's a dative bond, or also known as coordinate bond, and it's when an atom or a molecule has extra lone pairs of electrons and another one doesn't. It's deficient, so it will give its extra lone pair to the deficient molecule. I'm gonna give you all the list of examples and exceptions later. And so that's, now we already said all our bonds, and now we have to define something called the coordination number. And this number is basically the number of ions/atoms surrounding an ion or atom in a lattice or in a crystal lattice. And let's say you have here, it's supposed to be a 3D structure. In NaCl, they're gonna give you a 3D shape. Like you go check your central atom and see how many things is it bonding with. Most times, if it's in a cube, it's gonna be bonding with 6. So look, let's say we have art class now. A cube. and it's here. It can be bonding with one onto the back, one onto the left, one onto the right, one onto the front, one up, and one up down. So that is 6. In that case, the coordination number would be 6. Moving on to the next thing, we have our dot cross. We already know how to do a dot cross. I'm just going to be like giving some quick reminders. When you're doing a dot cross between, which is a covalent bond, they are 2 circles and the shared electrons go here in the middle. And always, even if you have the same species, please just make sure one of them is dots and the other one is crosses. In the middle you put dot cross. Like for example, hydrogen. I'm just going to give a very easy example. H, there's dot and cross. Now when it's double bond, you in the middle here, you're going to have dot cross, triple dot cross, dot cross, dot cross. Simple as. Now, when you have an ionic, you're going to put it between brackets. And here you're going to show, like let's say you have Mg, it's 2 plus. And here you have O, 2 minus. Actually O, and it's 2 minus, right? So you're gonna show, like Mg is gonna lose 2 electrons. So here you're gonna have an empty shell because the last shell is empty, it lost it. Here you're gonna have this, and then you're gonna add the 2 crosses from Mg here. That's how you do it in ionic structures, and that's it. Now our next point we need to talk about is Lewis structures. Now I know different teachers teach different ways, but I'm gonna teach the way my teacher taught us, which is, let's say we have, I'm gonna use a simple example, and I'm gonna start with the simplest example actually. H2. What you're gonna do is basically, now H2 and HE are the only 2 that follow duet rule, so I'm not gonna do it. H2 is just H dash H. Now when you study chapter 4, they won't really let you, in chapter 4 they won't let you draw it the way I'm gonna draw it now, but I'm gonna explain that in the chapter 4 summary video, because we're taking also Vesper and we need to draw it by the Vesper shape. But I think if they ask you for just Lewis structure and they don't mention any, honestly, even if they don't mention Vesper, I would really, it would be way better if you actually draw it with Vesper. Always. So you don't, you guarantee your marks, you know? Now, I'm gonna find an example to do Lewis structure on. Okay, yeah. So let's do it on NH4. A good example. You have NH4 plus as our example. First of all, I'm gonna want you to put the N in the middle. Then you're gonna draw single bonds all around it. H, 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 H. And then because it's plus, you're gonna put the plus around it. Now I'm gonna change the color, and we need to count. First of all, you need to look at NH4, the molecule, this. N is in group 5, so you put 5. H is in group 1, but there is 4 of it, so it is 4. Here you have, add them. 5 plus 4 is 9. But here you have a plus, so you subtract 1, so you get 8. So now you need only 8 electrons to be in this figure. Here you have 1 electron, 2 electrons, 3 electrons, 4 electrons, 5, 6, 7, 8. And that is correct. Let's move on to a different example. Maybe one with uneven charge. Okay. Now let's see, we have ClO3. And it's minus. Cl is in group 7. Actually, first let's just Cl, O, 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 O. This is in group 7. We're gonna need to change the color to tackle it. So ClO, Cl is in group 7, O is in group 6, but we have 3 of it, so 6 times 3 is 18. And then you have a minus here, so you add 1. So 7 plus 18 plus 1. So it's 8 plus 18, which is gonna be 24. Wait, not 24. Isn't it 26? Let me check. 8 plus 18 is 26. Okay, so now that we have 24, we also need to be careful of one thing. Whenever you're doing Lewis structure, you need to satisfy octet rule, which means each atom should be surrounded by 8 electrons. So there's obviously exceptions, but those we get to later. So we need to satisfy octet first. In the exam, don't just put a point, actually draw a circle. And don't leave it blank, fill it in. Now, let's count how many electrons do we have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh wait, that's Cl, my bad. That's not a mistake we're supposed to make. Let me start again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Now, actually guys, my bad, I counted them wrong. It's actually 28 electrons. I don't know how I counted wrong. Anyways, now we have here 28 electrons. And I have chosen, so it's 28 electrons. Right? But we need 24. So we need to get rid of almost 2 pairs. How do we do that? Whenever you see you have extra, I want you to take away 2 from any molecule and then take away 1 from Cl. What do you do in its place? You add a double bond. So let's count again. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Oh wait, so we did have 26. Yeah, so now we have 24 and the double bond here. So, yeah. And then you need to add the brackets and the minus. Anyways, now we have CO2. Actually, let me change back the color. CO2. C is in group 4. O is in group 6. And you have 2 of it, so it is 12. Add them together, you get 16. Now, C, then you do single bonds, O, O. By the way, in the exam, do it with pencil. It's going to save you a lot of sanity. Because you can't keep scribbling. So now let's count. You have 2, 4, 6, 8. Then here's 16, then you get 18, and here you have 20 electrons. You need 16. So you need to get rid of 2 pairs. So you're gonna remove 2 from here, add the double bond, and remove 2 from the C. Whenever you remove 1 from a side atom, you remove it from central. And that's, we removed 1 pair, which means we remove another 2 from here and 2 from here, add the double bond again. So you have 2, 4, 6, 8, 10, 12, 14 and 16, and that is correct. Now I'm gonna do one more example which has a triple bond like N2, which is just N, M, group 5, so you need 10 valence electrons. We need to satisfy octet before we start anything. And then you have 8 here and 8 plus 6, which is 14 electrons. We need to get rid of 2 pairs. So you remove 2 electrons from here, 2 electrons from here, add the double bond. Now you have 2, 4, 6, 8, 10, 12. Still you have too many. You remove an extra pair from here, and a pair from here, and add a triple bond. Now you have 2, 4, 6, 10. 2, 4, 6, 8, 10. And this is correct. So that's it for my summary, like for Lewis structures. I'm just going to give the exceptions to the Lewis structure rule because there is some exceptions. And yeah. So our exception. Okay, so exceptions. Number 1 is species with odd number number of valence electrons. For example, NO. Here you have 5, here you have 6, which is 11. Now when we want to draw it, you're gonna get NO 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Anyways, now when we try to draw it, now we have 8 on this one, 6 on this one, we have 14. We need 11. So we need to remove 2 from here, 2 from here, add a double bond. We still have 12. So what you're gonna do in this case is remove an electron from N. And this is one of your exceptions. Now then, your second exception is electron deficient species. And that means now, or compounds قصدي. Wait. Now in this case, what I've seen is they usually come from group 3 and 5, but don't take it as a rule. For example, our biggest example is, let's say, BH3. You have B, 1, 2, 3, H, H, H. Boron is a metal in group 5, if I'm not mistaken, but I have my periodic table, so let's check. Yeah, boron is in group, 3, sorry. Since it's in group 3, anyways, 1, 2, 3. Oh wait, hydrogen only does not have any. So now we have in group 3 and group, and also 3. Add them, you get 6. Now you have 1. Now when you count the electrons, you have 1, 2, 3, 4, 5, 6. So you're gonna say, what the hell am I supposed to do with this? Just remove it. And this is how you draw BH3. And now for our last exception is, I think our last exception. Yeah. Elements with expanded orbitals, or sorry, expanded valence shells. But this is in one case and one case only. Only if valent or central atom is in period 3 onwards. So it has to be in period 3 or anything under that. And one example is just SF6. You have S is in group 4 and F is in group 7 times 6, which is 42. You add them, you get 48. S in the middle, you have 1, 2, 3. Actually, it's supposed to be drawn 1, 2, 3, 4, 5, 6. F, 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 F. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Then you have 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. And this is correct. And that's it for our exceptions. So now we're going to move on to our next topic, which is just pi bonds and sigma bonds. Whenever you have a single covalent bond, it has one sigma bond. When you have a double covalent bond, you have one, I forgot how to draw the sigma thing, sigma 1 pi. And when you have triple covalent bond, you have 1 sigma and 2 pi. And that's it. And what's it called? Whenever you see two molecules that are joining together in a straight line or like beside each other, or two orbitals, this is sigma. Whenever you have, let's say, an orbital like this and an orbital like this, they're not end to end, this is pi. Now, we're done with now we have resonance structures. Now let me quickly explain what's resonance. Resonance is when you can, like, when you have a double bond that can be moved around. So let me give an example. We have, for our resonance, we have an example which is, I'm gonna just say, CO3 2 minus. CO3 2 minus, let's draw it out normally. You have C, and then let's just let's first, like, this is in group 4. This is group 6 times 3, 18. 4 plus 18 will give us 22. 22 plus 2 is 24. Now, when we draw it, you have to draw, of course, you fill out. Now here, when you count them, here you have 8, 16, 24, and plus 1 here. So this we can't have. So we're going to remove it and remove 1 from any side, and you're going to add a double bond. But couldn't you remove it from the down one? Couldn't you remove it from the left one? Yes, you could then. So you could have 3 structures, which are C double bond here, or C double bond here, and just single bond here and single bond here. These are all 3 possible explanations. So what you do is you just redraw it with a straight line and a dotted line, straight line and a dotted line, or like, because it's trigonal planar, dotted line, straight line with a dotted line, and then fill in the O, and then you add the brackets, of course, and the 2 minus. This just means that the double bond could be any of these places, and it's a resonance structure. Now, there is some exceptions to there's not, not exceptions, my bad. There are molecules that have resonance, and I'd prefer if we memorize them, because who's actually, like, free to do them in the exam? The example, the ones with resonance are NO3 minus, HONO2, SO2, CH3, COO minus, SO4 2 minus. You have NO2 minus, N3 minus, CO3 2 minus, O3. Then you have C2H6. Then you have PO4 3 minus. These are all the ones that have resonance. And we also have ones that have dative bonds. Now, what's a dative bond? I already explained. Dative bond is when you have an extra pair of electrons that you're willing to give. So let's say, for example, PH4 plus. Here you have P. When you draw PH4 or PH, let's draw first PH3, because the plus comes from the extra hydrogen, right? Which is an extra whatever. So now you have, because it's usually like this, because P is electron, it has just like, this is the structure, what I'm trying to say. Now here you have a hydrogen that's here. This hydrogen needs 2 electrons, but it doesn't have any. So P is going to be kind and share them with hydrogen. And that's how you draw it, by the way. You don't have to draw it curly, you could just draw it straight up and the H. And of course you need to add the brackets and plus. Now I'm going to give you the exceptions, or the ones that have dative bonds. The ones with dative bonds, memorize them again, makes your life easier, are NH4 plus, BF4 minus, H3O plus, PH4 plus, and Al2, Cl6. And these are the ones with the dative bonds. And that's it for the dative. And yeah, and now we have, I'm just gonna like talk about two more topics and solve a few CQDs about the last few topics. Now we have bond energy and length. All I'm gonna tell you is the greater the bond energy, the greater the bond length, the lower the bond energy, and the more reactive. Because the lower the bond energy is the more reactive part. And whenever you have a single covalent bond, it has the shortest bond and the bond order of 2, bond order of 1. Bond order of 2 is double covalent bond, and it's the second. H1 is the longest. This is second, and the triple is the shortest because it's the strongest. And it pulls in, and it has a bond order of 3. And that's it. That's really much all you need to know. And for formal charge, you just need to memorize a small equation. Formal charge's equation is, you see group number or number of, no, actually it's group number minus the lone pairs minus half of the bonding pairs. And always when you do for an entire molecule, the sum of all the formal charges must equal the charge of the atom or the compound or the molecule, And that's it for formal charge. Now I'm gonna go to the CQD document to solve a few questions. Okay, so this is part of 3.5, and I'm gonna be explaining quickly. I'm gonna be explaining using these 3. The rest's easy. In all of these cases, you're gonna need to find when you have a percentage, you divide it by the molar mass, then you find the number of moles, and then you find the number of moles for all of them. The lowest number of moles, you divide it by all of them, and then you get whatever I'm gonna show you in this question, but it's one of the hard types of these questions, or not hard, really long. You just need to understand it. So you have a compound that only has these 4 atoms. Combustion of this many grams of this compound produces this much CO2 and this much H2O. So this compound X plus O2 forms this much of CO2 and this much of H2O. Now, when you have the mass of something, can't you find the moles? Because mass over molar mass gives you the moles, right? So divided by 44 for here, divided by 18 here. So here you have moles equal to 4.84 times 10 power negative 3. And here you have, later we'll do this. So now you have this many moles of CO2. Now, how do you find the mass of carbon? To find the mass of carbon, you multiply this by the molar mass of carbon. So this times 12, you get 0.0581 grams of carbon. Then you divide it by the total mass, which is the, not you're gonna say which is 2.03, no, of the compound, which is 0.157. Then you're gonna find carbon to have 37%. Then you're gonna do the same with hydrogen, but here you're gonna find the moles and multiply it by 2. Why? You're gonna ask me why. Here you can multiply by 2 because you have 2 atoms of hydrogen, because hydrogen is diatomic. So you're gonna find that 1 mole is equal to 3.44 times 10 power negative 3, and you're not gonna multiply it by the mass because it's already times 1. Then you're gonna again put it over the total mass, which is 0.157. You're gonna get it to be 2.19%. Then they gave you that you reacted it again with NH3, this much of NH3. So you're gonna do the same exact thing. So you have NH3, you're gonna find, what's it called? You're gonna do 0.203, 0.0230 divided by 17, which is the entirety of NH3. You're gonna get that you have 1.35 times 10 power negative 3 moles. Then you multiply this by the mass of nitrogen times 14, and then you get 0.0189, again divided by total, which is divided by 0.15, which isn't 0.157, this time it's 0.103 because this is a different reaction. 103, you're gonna get that it is 18.4%. So now what are you gonna do? You're gonna take all your percentages, which I'm gonna underline, highlight in blue, this percentage, and this percentage. You're gonna subtract them all from 100. You're gonna ask me why? To find how much oxygen, or the percentage of oxygen. So when we do that, 100 minus all percentages, you get that there's 42.4% left for carbon. Now I'm gonna need you to take all your percentages and what they're for and draw a small table. We have carbon, hydrogen, nitrogen, and oxygen. Carbon, hydrogen, nitrogen, oxygen. Carbon had 37%. This had 12.19. This had 18.4. This had 42.4. Now I'm gonna need you to divide all of these percentages by the molar mass of each atom. So divide by 16, divide by 1, divide by 14, divide by 16. This is 12. I mixed up. And then you're gonna find the mole ratio, which is 3.08. Here it's 2.19. Here it's 1.31. Here it's 2.65. You're gonna find which one of these numbers is the smallest. We know that it is 1.31. So we're gonna divide all of them by 1.31, divide by 1.31, divide by 1.31, divide by 1.31. Here you're gonna get to be 2.35. Here you get 1.67. Here you get 1. Here you get 2. Now we cannot ever have a fraction. So you're gonna multiply it by 3 numbers until you get all of them whole. You're gonna multiply it the first time by 2. If you get a whole number, you stop. If you don't, you multiply it by 3. If you get a whole number, you stop. If you don't, you multiply it by 5, then you should get a whole number. Here, this case, I tried them, you multiplied by 3, and all 3 of them will give you a whole number, so times 3, which is 7, times 3, which is 5, times 3, which is 3, times 3, which is 6. So now you have C7, H5, N3O6. And that's your answer. Like I said, not that confusing, just very long. Anyways, I'm gonna remove it and solve the grid now. Now the grid after it is way easier than this, of course. I doubt this question is coming. I just had to explain it because it's the hardest. Now the hydrocarbon with a mass of 3 underwent combustion producing, okay, so you have a hydrocarbon, we're gonna name it X. It has 3 grams. It went under combustion, which means plus O2, and formed carbon dioxide, which is 5.5 grams. Now, if the carbon all converted to carbon dioxide, what's the percentage of carbon by mass? So again, what are you gonna do? You're gonna find the mole. So 5.5 divided by 44. And then you multiply it by the molar mass. You could do it all in one step, which is 12. Okay? So you're gonna do this, you're gonna get 1.5. So now you're gonna take 1.5 over the whole mass of the sample, which is 3. So 1.5 divided by 3 is gonna give us 0.5 times 100 is 50%. And that's our answer. It's very easy, this one, see? Short. Now for these, I'm just gonna, like quick read them because we took them before and I'm just like revising them. And one thing, you never ever ever put any prefixes for ionic compounds. Just saying. And for yeah, forget. Anyways, so oxygen difluoride is OF. Then di means 2, so OF2. Magnesium oxide is ionic, so it's just gonna be Mg is in group 2. So and oxide means oxygen, which is in group 6. One has 2 plus, one has 2 minus, so they cancel out. Sulfur hexachloride is just sulfur, and then you write chloride, and hexa means 6. Ammonium nitrate is gonna be ammonium and then nitrate. Ammonium is NH4. These are both ionic, so you need to like beware for their charges, but they're both +1 and -1, so it doesn't matter. NO3. Magnesium 3 chloride, which means MgCl3. Lithium hydrogen carbonate is just LiHCO3. Calcium hydroxide CaOH2. You're gonna say why OH2? It's because Ca is 2 plus, OH is minus, so it's cross, the crisscross method. Yeah. Here, just name these. This is ionic compound, so you don't put any suffixes. It's just sodium sulfate. Here, I'm just gonna continue writing them. This is aluminum bromide. It is this is not ionic, so we can put, so it's diphosphorus pentoxide. Now this is nitrogen monoxide. Here you have CaCO3, which is calcium carbonate. Here you have copper 1 chloride. Now you're gonna say, why is it 1? It's copper 2 chloride. You're gonna say, why do you put 2? Because it's a transition metal. When it's a transition metal, you need to put the state symbols in Roman numerals. Here you have iron 3 oxide. You're gonna say, how do you know it's 3? It's because it gave the O3, so it is 3. Here, which of these have I predict the formulas? So Mg is 2 plus, N is 3 minus, so it's gonna be Mg 3 and 2 because you crisscross. Al3 plus, O2 minus, Al2O3, Li plus and O2 minus, so it's Li2O, Ca2 plus, F minus, so it's gonna be CaF2. And here it's just gonna be quickly, this is anhydrous because it's not chemically combined to water. This is hydrated because it is chemically combined to water, which you can tell by the dot here. The name of the water molecules are called waters of crystallization. And here, what to do, you just need to find, you do this number and you subtract it from the molar mass of the compound. Then you're gonna get your mass. The mass, you do it, this mass, which you're gonna get actually to be 90, you put it over the molar mass, which is 18, and you get your number, which in this case is 5. Cu is always gonna be, CuSO4 is always gonna be 5. CO, which is cobalt chloride, is always gonna be 6. Just memorize these because they're essential. And that's the end of this video. Hope you understood everything. Have a great day.